So hello everyone, welcome back to our channel 5, and today we're going to discuss about current electricity. So what are the two key components we require for current electricity? They are, first is cute little blue electron, that is the most key component containing charge, and another is time. So earlier we have studied about where the charge has been fixed with some kind of potential. So here it's gonna break out that potential and will start moving. So it will be coming out from its static condition and will start to flow. And we have to measure that. So that will be the electricity. How can you measure current? As you can see here, you and the electron is standing still. Now both of you starts moving in same velocity. So, with respect to you, it will seem that the charge is at rest and hence you cannot measure the current. But if the charge starts moving and you are at rest, then you can measure the value of current when the charge starts flowing within a conductor. So, as you can see here, this yellow piece of conductor which is connected with the battery with its positive and negative terminals. I have only shown only 3 electrons just to simplify the system and to show how the electron move when a potential is applied. So as you can see here, the electrons right now move from minus terminal to the positive terminal. Why is it so? The positive terminal is deficit of electron, while the negative terminal is excess of electron, and thus it travels from lower potential region to higher potential region, that is considered for the positive value of potential which is higher and negative value of potential which is low. And thus with a constant potential difference, the electron starts traveling along from negative potential to positive potential. Here we consider uniform velocity of charge for steady current is produced. But we all know, right on the time when the charge starts to flow, it begins with zero velocity and slowly it attains its velocity and reaches a constant velocity. But the journey from zero to constant velocity is neglected out in our study right now in this topic, and we directly consider the steady velocity part so that we can achieve a steady current and do all our study and calculation. So thus the equation for current will be I equals to Q by T, that is rate of flow of charge per unit time, and the SI unit will be shown in ampere. So now what is Ohm's law? So first you can see here a conductor connected with a cell with positive and negative terminal, and the cell provides a potential V. So two equations that appear on your screen, one is V proportional to I. So let me make it more prominent. So V proportional to I. So with respect to that, we write V equals to R into I. So thus R will be a proportionality constant, and it is also known as the resistance of a conductor. So what will be the resistance of a conductor? It is the property of a conductor by virtue of which it opposes the flow of current. So as you can think that this man is the resistance within a conductor. So thus when current starts to flow, this is the man who resists the flow of current, that is the electron. So this will be the man, he is going to guard the electrons and not let it go, or it is going to make difficult for the electron to travel along the conductor, and thus this man will be known as the resistance. So this property is generally known as the resistance of a conductor. So to measure this formula, to obtain the Ohm's law, we must keep in mind these two following points. That is, the flow of current should be considered steady, and the temperature and other physical conditions of the conductor should be remain same. So this last point is quite important because it determines the nature of the conductor and also the value of resistance within the conductor. So one question that drops at the bottom of the screen, that is to plot V versus I curve and what will be its nature. just pause the video right here and try to obtain the nature of the curve. So if you couldn't make the curve, just see the video of graph that has been linked at the top of the screen. So then, how the resistance of a conductor varies. First point, that will be the temperature. So as you can see here, this is a piece of conductor and few electrons are present. This blue line, as you can see, these blue lines are the random motion of the electron, and as I have said, it is a random motion, so it will be along any direction. So if we put potential, so let us consider that we put a potential of positive along this side and negative along this side. So thus the electrons will start traveling from negative end to positive end. But as we increase the temperature, this random motion increases, and thus by chance an electron has a tendency to move along this direction. Some other electron with its random motion gonna hit this type of electron, and the motion of path for this electron changes to another direction, and which affects the motion or the flow of electron, and it decreases the flow of current. So in this way, the randomness of the electron increases as it starts colliding among themselves with increase of temperature, and so with increase of temperature, resistance of a conductor increases. So the formula or the variation with which resistance of a conductor increases is as RT equals to R0 1 plus alpha T, where alpha stands as the temperature coefficient and T stands as the temperature at which we're gonna obtain the resistance. So RT is the resistance at temperature T and R0 is the resistance at 0 degree centigrade. So at the bottom of the screen, a question has been asked to obtain the relation of alpha from the above equation. Pause the video right here and try to obtain this equation. It will be quite easy to obtain this kind of equation. So as we know that with the increase of temperature, the resistance of a conductor increases. Thus we can say that alpha must be positive for resistance as the value of resistance increases with temperature. But do you know that for semiconductor, the resistance decreases with increase of temperature, and hence alpha will be negative for semiconductor. Semi, just mention semiconductor. So now, what are the other physical conditions that affects the resistance of a conductor? That is the material and dimensions of conductor. So we consider a conductor made up of same material and it is uniform in density, and thus it will be same considered, but the dimensions can be varied. So as you can see in this yellow block, the resistance is proportional to the length of the conductor. So the resistance must be proportional. So how it is possible? So resistance proportional to L. So let us consider that electrons required to travel all along the length of the conductor to reach from one end 1 to end 2. So as the length increases, the path of travel for the electron increases, and thus the resistance increases. Now, resistance is inversely proportional to the cross-sectional area of this slab. So R inversely proportional to area. So when electrons are traveling from point 1 to point 2, they are not alone, but there are a huge number of electrons. So as the area or the cross-sectional area of the slab increases, so it will be much more easier for the electrons to have less collision among themselves and can travel from point 1 to point 2 easily. And thus with increase of area, resistance decreases. And hence we obtain the formula in form of R proportional to L by A, or R equals to rho into L into A, where rho is the proportionality constant, or also known as resistivity of a conductor. So then what is the resistivity of a conductor? So let us consider L equals to 1 and A equals to, that is area equals to 1, that is unit length and unit area, and hence the resistance of a conductor when length and area are unit will be the value of resistivity of that conductor. I repeat it, that if we place L equals to 1 and area equals to 1, then R equals to rho, and hence that will be the value of resistivity of a conductor. And thus the SI unit of rho will be ohm into meter. What will be the state of electron in absence of electric potential? So as you can see here, this blue color are the electrons, and again here these arrows states the random motion of the electrons. So here the electrons have velocity u1 as the velocity of first electron, u2 the velocity of second electron, and so goes on for all the 6 electrons. So when there is no potential, the electrons are continuously in motion but in random motion along all possible directions, and they are under constant collision with each other, and thus we can say they are in random motion in all possible directions colliding with each other. But if we try to obtain the average velocity or the net velocity of all the electrons, it will be a big zero because it is in random all possible direction, and thus we can say that there is no net flow of charge without the presence of any electric potential. Or you can consider similarly as your class without any teacher. Randomly, you all are shouting and running here and there in the class, and ultimately the class is going with zero amount of studies. So the state of electron now in presence of electric potential. So last we have studied when there was no potential is present and randomly moving here and there. But now here a V potential is applied across the end of the conductor, and thus this end having a V1 potential and this end having a V2 potential across the conductor, and electrons must be moving from negative end to positive end. So this will be the direction of the movement of electron, and this opposite direction will be the flow of current. So with the application of the potential, the electron starts accelerating and moving from negative end to positive end, and current is produced. So let's study what will be the number density of electron. We consider small n as the number density of electron. Okay, so what is it? Let B capital N be the total number of electron within the total number of electron within the conductor, and thus divided by its volume, that will be area into length of the conductor, will be the number density, and hence we obtain the total number of electron as number density with area and length of the conductor, or the total charge within the conductor will be Na L into E. This is the total charge that is comprised within the conductor. So thus the total current will be total charge, that is N A L E divided by time as the rate of change of charge flowing, and hence we can obtain it in the form of N L E. So for L we put the T just below it and A, and thus we obtain N E A into V, which will be the velocity of the electron with which it is moving, and thus we come down to the average velocity of all the electron with which all the electrons are accelerating and moving towards from negative to positive end. Hence, what is current density? So the current flowing through the conductor per unit area. So as you can see here, this yellow colored conductor where current I is flowing along this direction. It has been directed already, and A is the area of the conductor. So current density is determined with the term J, and thus with respect to the definition we can obtain as I divided by A. So thus the SI unit will be in ampere per meter square for the current density. But could you guess that current density is a vector term? So how is it possible? So current density will be a vector term. It is possible due to the direction of this area. So what is the direction of an area? So let us consider area as such a plane, and thus the normal direction n cap is the direction of this plane, and this n cap contributes for the vector of current density, and thus J is a vector quantity. Now let's obtain the value of J, and that will be, as we have obtained the formula of current as N A E into V divided by A, and thus we obtain as N E V as the final formula of current density, or this will be the magnitude of current density. So as you can see here, it's a vector quantity. Now drift velocity. So as I have already said, we measure the average velocity of the electron, and thus the average velocity with which all the electrons are moving are represented as drift velocity, and that is in presence of the electric field. So why we name it as drift velocity? So the initial velocity with which all the electrons was moving, that was denoted by u1, u2, u3 and dot dot dot. And with the presence of the electric field, when all the electrons are accelerated, they achieve a final velocity, that is the v1, v2, v3, and the average of that final velocity is the drift velocity. So as you all know, this kind of equation, that is v equals to u plus a t, this we consider separately for all the electrons, and thus we're gonna obtain v1 as v1 equals to u1 plus a into t1, then v2 equals to u2 plus a into t2. Can you guess why this a term is kept simple for all the cases? This is because all the electrons are accelerated due to the presence of same kind of field, or due to the same amount of force. How? Let's see. F equals to E, that is the charge of the electron, and this is the capital E, that is the electric field present due to the potential V. So now F equals to mass of electron into acceleration is equals to E into capital E. Thus the acceleration will be small e into capital E divided by m e, and this is the value of acceleration for all the electrons. Okay, now to obtain Vd, that is Vd equals to v1 plus, sorry, getting stuck, v2 plus v3, then dot 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 dot, and divided by n. So we replace it as u1 plus u2 plus u3 divided by n, and then plus as a into t1 plus t2 plus T3, then dot 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 at the n terms, then divided by n. So now, can you guess why the first term will be, this first term will be denoted as 0? So hence this term will be equal to 0, and this term will be denoted as, a into tau. So why the first term is 0? As we already know that initially the average velocity when there was no potential present was 0, and thus u1 plus u2 plus u3 divided by n, that average velocity will be 0. And now for the next term, where we write a into tau, where tau is the average value or the average value of time, which is also known as relaxation time. RELAX, relaxation time. So what is relaxation time? The average time between two consecutive collisions will be relaxation time. So now let's change the color of the pen and try to obtain VD final. So VD equals to, replacing it with alpha as E into capital E divided by M and multiplying tau. So this is the expression of the drift velocity. So this is an important expression which often comes in form of numericals, and this expression shows that VD is proportional to the electric field that is applied across the conductor, because small e, m and tau will be constant. So thus the value of current will be, or the expression of current that can be obtained will be NA E into V D, that is the drift velocity, and thus NA E, then VD is replaced as E capital E divided by M, or it is written as N A E square capital E divided by M. So this is also an important formula of current, which is quite different than the term that we have used. Oh sorry, I missed tau right here. So tau will be here. So now further we have to obtain the formula of resistance. So how this can be obtained? As we have got that I equals to N E square A E into tau divided by M. Now we know E equals to V divided by L. V is the potential and L is the length of the conductor, and thus we replace it here as N E square A divided by M, then tau and V by L. And hence if we keep all these terms in bracket, and tau divided by M L into V, so I equals to, keeping all these terms, as we know that I equals to V divided by R. So we can equate, so let me change the color of the pen. Thus we can equate R with this term and can obtain 1 by R equals to this whole term in the says, and therefore R equals to will be ml divided by n e square a into tau. And hence this is also an important formula to remember. We have obtained as the formula of resistance that completely depends on the dimension, relaxation constant, area, that is also comes in dimension, mass of electron, and all these terms, and even the number density. So it completely depends on the nature of the conductor. And now finally, so let me change again the color of the pen. And so finally we have already come to know that R equals to rho into L divided by E, and hence we can obtain the value of rho as rho equals to m divided by n e square tau. Just simply comparing these terms with this equation, and hence we again obtain an important formula, that is the resistivity of a conductor can be expressed in this form. With this term we can also obtain conductivity, that is sigma, expressed as 1 by rho of a conductor, and thus we obtain n e square tau divided by m. So this is also an important equation. And so in this page we obtained four equations. First was this, the formula of the current in terms of potential and all, then the formula of the resistance, then the formula of resistivity, and finally the formula of conductivity. So today video ends here, and next day I will be coming up with much more topics on current electricity. Thank you.